Well, hello. Today we'll have a quick look at resistors. Again, we'll use the multimeter to do some measurements on resistors, but I thought I'd just start the video by giving a little introduction to what resistors are. So in the last video we looked at a battery. A battery has a symbol very similar to that. And the battery, of course, is in volts, so we have some volts, however many volts it is. We have some amount of current, so the current might flow through here. Current is typically indicated using the letter I, but I'm going to stick to using A in these examples for amps. Might be a small amount of amps, in which case we'll use milliamps. Might be a large amount of amps, and we'll use amps. So we have two components here. We have voltage and we have ampage. With voltage and ampage, we can determine power. Power, which is in watts, is equal to volts times amps. So if we have example 10 volts times 1 amp flowing in our circuit, that equates to 10 watts of power. So that's simple enough, hopefully. The next component we need is to actually put the power into something, and the power is usually put into something like a light bulb, a heater or electric motor. There are other devices such as speakers, but all of these components need to have some form of resistance, and of course resistance is given in the symbol omega, which is ohms. Okay, so we have three components here. Voltage, we have current. If you think about voltage as push or water pressure, and ampage as the amount of water flowing. So you could have one tap with a push, that's the voltage. You could have a small hose pipe or a small wire that lets a certain amount of ampage flow through it. If too much pressure builds up in it, the hose will swell or attempt to get bigger. It will constrict the flow of water. Just the same as if our wire is not big enough, it will constrict the flow of ampage. And the constriction is actually ohms itself. So at the end of the hose you might have your kind of spray pattern nozzle, and that restricts the amount of flow. You can also turn it off there, and that's a varying ohmage. That takes us on to, of course, Ohm's law. We won't go too much into Ohm's law, but essentially if we know any two of these components, voltage ampage, voltage ohms, ohms amps, we can actually figure out what the other component is. And we do that using Ohm's law, which is V over IA. Like, I've done that wrong because I've switched A for amps, so that's completely wrong. V over I ohms. That's traditionally how it's written, but I am going to be using A. Okay, for amps. So what we can do here is we can actually divide the voltage by the amount of amps, and that works out our resistance. We can times the amp by the ohms, and that will give us the amount of voltage, or we can divide the voltage by the resistance, and that will give us the amount of current flow. So we could do an example. I'm going to do a quick example and then we'll actually test it to see if it works. So I'm going to use, what shall I use? I'll use my big 12 volt battery. Big 12 volt battery. 12 volt. And I want, we'll set the resistor up and then we'll calculate how much current is flowing. So here's a resistor, and I actually want quite a large resistance on here because I don't want to burn anything out. So let's do that measurement. So as mentioned, we'll just cover that up for the moment. This is my rheostat. It's basically a big old resistor that we can vary. Can bring it from one end to the other. There are 3 connectors on it. One connector here, one connector there, and one connector on the bar. So what I'll do is connect at one end. Switch it around there. We'll connect at this end here. I'm going to roughly screw in my connection terminal there. I'm going to make sure that I am connected to ohms, which I wasn't. Okay, before every start. It's fallen out, not a good start. I'll connect this up to the other side of the rheostat. I will set this up to ohms. It was set to ohms. Yeah, you can see that. So currently we are set to 12 ohms. And if I slide this a bit further up, you should see that increases. It increases to about 15 ohms. Down the other end, if I bring it all the way to the closer end of the connector, I am reading a much lower ohmage, 0.4. Will it go to 0 ohms? No. 0.2 ohms. And up the other end, we can have any ohm value or any resistance value between 0.2 and 15.3. So let's set this to 15. Not quite. There we go, 15 ohms. Brilliant. So let's put 15 ohms into our little drawing, and we'll use Ohm's law to actually calculate the amount of current flow. So find my pen. We know our resistor is now 15 ohms. Don't be ashamed to write down Ohm's law every time. You can see the first time there I actually got it wrong, but that's because I substituted A for I. So V over A R. And using Ohm's law, well, I've got voltage, I've got ohms, so it's going to be 12 volts over 15 amps. And this is always in amps. If it's milliamps, you've got to write that 15 as a small number. So if it was 15 milliamps, it would be 0.015 of an amp. Some of you probably don't want to get your calculator out to do that. You can do it mentally. But I'm going to do that using the calculator. 12 divided by 15 equals 0.8. And that will be 0.8 amps. Okay, so not quite 1 amp. So do we believe that's true? Are we going to believe a calculation that 15 ohms here connected to my 12 volt battery is going to give me 0.8 amps? Well, let's try it. I will take that connector off and just pause this video while I move the battery over. So I've got everything I need here now. I've got my resistor, it's still set to 15 ohms. I have my multimeter. I have my 12 volt battery at the back, and if you've just watched the last video you'll see that was about 12.12 volts, so close to 12. I also have some saltwater crocodile clips and some banana type test leads. There we go. So trusting me here, I'm going to connect this one to 12. Now I will once again remind you that you never want to short circuit a battery. Do not connect negative straight to positive. Do not use your multimeter on the current setting, which I now need to set this to take a reading. Do not connect your multimeter up without a suitable resistance. Okay, if you do, you will get sparks, you will get smoke. It usually happens to an engineer, electronics engineer in the early days. I tend to try not to blow stuff up now because it is expensive, but if you guys want some stuff blown up for YouTube electronically, we could have a go. So I'm going to take my negative, shouldn't have these wobbling around loose in case I accidentally touch something, but we'll get those connected up, and I'm going to connect my positive. Now the positive is going to go to the other end of my resistor down here. I'll get that on there. Yeah, no, yeah, come on you saltwater crop, there we go, it's on there now. The other end of the resistor comes and connects to this probe. This probe needs to complete the connection by connecting to there. And you'll see I get no reading. Can you tell me why? That's right, I didn't set my multimeter to amps, and it won't actually give me a reading unless I set it up properly. And now if I connect that to there, How much am I reading? 0.748. So 0.478. It's pretty close. It's not exact. It's not exactly the resistance we wanted. And if I could find my pen, which I've now put down, I would write that down. So, where shall I write this down? I've run out of space down here. But it is 0.74, and it's dropping, so the battery's on its way out, amps. Can anyone think of any reasons why the actual red resistance is lower than the voltage calculated using Ohm's law? That's right, I heard the correct answer back there somewhere. Ohm's law is in an ideal world. We have got just 15 ohms from the resistor. But realistically, actually, we have got some resistance in the wire, some resistance in the saltwater crocks, we've got some resistance in the battery itself, resistance in the meter if I didn't cover that already. So actually we've got a little extra resistance there. And if we used Ohm's law now using this number, we can actually figure out how much resistance is in the circuit. Let's do it, why not? Maths is kind of fun. Okay, so here's another piece of paper. The current that we measured in the circuit was 0.745 amps. We had a voltage of 12.12 volts. So there was a slight variation in the voltage as well. Using Ohm's law, VAR triangle, we take the voltage, we divide it by the ampage, and that will give us a resistance. So let's do that now. 12.12 divide by 0.745 equals 16.2, and if I round it up, 7 ohms. So we were thinking that our resistance was about 15.01. So there is a total resistance of 1.08 ohms inside the meter, the leads, and everywhere else. Okay, so all the places that we've not measured, there is an extra 1 ohm. Some of the other things that might be happening is the voltage might be dropping when we're loading the battery, and if I wanted to test that, I'd need another meter measuring the battery, and I'd actually take a reading from the battery as I take this reading, so I've got two real-world readings. So something to remember, when you use Ohm's law to roughly calculate what everything should be in the real world, but actually in the real world things don't behave how they should. You know, batteries are not always giving as much power as they should, connections should not be, not as clean and nice as they should. Gold connectors would help, really good quality copper cables would help, a really good quality multimeter helps with accuracy, but realistically there are all sorts of variations in the circuit that will give us a slight variance. But hopefully you can see, using some Ohm's law there, we could quite easily roughly predict our current flow, so 0.8 and 0.7. Now start to think about ampage times voltage into power. Things are going to start getting hot. 10 watts will get quite hot eventually. 5 watts, not too hot. If you think about, a 100 watt light bulb, the old incandescent bulbs, they got really quite hot very quickly. So what we'd actually do is try and calculate how many watts has been passed through that circuit. So that's going to be 12 volts times the 0.745 amps, and it's about 8.94 watts. So what does 8.94 watts mean? Well, I can actually take a little reading here. I'll get my temperature sensor, plug that in there, and then let's actually start conducting some power back through here. Oh, paper's gone, never mind. So there's our current flowing, 0.751 amps. And actually you can see the thermometer here, which was already acclimatized to this room, is increasing in temperature. 21.9, 22. So I have got a little electric heater here and it is just getting warm. And actually if I reduce the resistance, you'll see the current goes up. And if I get to 1 amp, I've got 12 watts. And you'll see that the temperature starts to go up a bit quicker. And if I bring this right down, so we've got 2 amps flowing, at 2 amps, because it is a 12 volt battery, 2 times 12 is going to be 24 watts. And 24 watts is enough to get toasty. There we go. Actually pop this in the other end, because that's the end that will be getting hot now. And you can see we've got 24, 24.3, 24.4. Of course, if we were building a circuit where we needed this amount of current flow, things were getting hot, we have to start trying to tackle the heat by using things like fans or heat sinks or other methods of dissipating heat. Or if you're the case of something that gets very hot, for example a heat plate or an electric heater, we'll need to use some sort of thermal insulator. So in this video we've had a quick little look at a variable rheostat resistor. We've had a little look at measuring resistance using the multimeter. So again, remember to ensure that your probe cables are connected to the resistance port and that you are set to resistance. You'll also notice, let's have another look at this, that if I connect these probes together, yeah, we're reading an internal resistance of about 0.2, maybe 0.1 on a good day. So that's showing that there is some resistance in this system. What we'll do now is have a quick look at some various types of resistor and how we'll go about measuring and testing that they're good.